So first, we now know, and we will put that into our model, that every time we perform a task, the duration is not exactly the same. So for example, when we perform task 1, the time to perform it is not always 3 minutes. We're going to admit some variability, which is represented by this value here, 20%, which means that we will have a uniform distribution in between two values, the mean minus 20% and the mean plus 20%. So in this case, the 20% of 3 is 0.6. So we'll have a range of durations for task 1 ranging from 2.1, which is 3 minus 0.6, to 3 plus 0.6 minutes. So every time we perform a task 1 for an amplifier, we are somewhere in between these two values here. The second thing, or prior to that, we can assume that if we do a set of tasks in a station, for example, in station 1 we were performing tasks 1, 2, 3, and 5. Previously, we were assuming that the total time was the summation of all those three values, and always we have a time which was 20 minutes. Remember that this was the cycle time of our production line. Now, times for each of these 4 tasks in station 1 vary. So every time we produce an amplifier, we assemble the amplifier in station 1 and we do task 1, 2, 3, and 5, we have different times corresponding to these uniforms. This is the uniform we estimated before, but we have 3 other distributions which are also uniform distributions. So for every single amplifier we produce in station 1, we'll have to get a number corresponding to this distribution, a number for this other one, another number from the third, and another number for the fourth. And when we sum them all, we have the total time for that amplifier in station 1. That means that we have different values corresponding to all 4 tasks, and eventually we have a different time for all 4 tasks performed in station 1, and the same goes for stations 2, 3, and 4. So that source of variability will have an impact on the capacity we actually have from the design we obtained from the optimization model.